Magnetic fields in current-carrying loops and in ideal solenoids is going to be the topic of this lesson in my new general physics playlist, which when complete will cover a full year of university algebra-based physics. Now, in this lesson, we're specifically going to talk about the strength of the magnetic field at the very center of a current-carrying loop and right through the center of an ideal solenoid. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. Now, if you're new to the channel, we've got comprehensive playlists for general chemistry, organic chemistry, general physics, and high school chemistry. And on chadsprep.com, you'll find premium master courses for the same that include study guides and a ton of practice. You'll also find comprehensive prep courses for the DAT, the MCAT, and the OAT. So we're going to start by looking at the magnetic field at the center of a current-carrying loop. Now, the current in this loop, as it proceeds around the loop, is going to be creating a magnetic field. And we learned that, for a straight piece of wire, it goes around the wire everywhere around it. But this thing's not straight. And there's a magnetic field created everywhere around this wire in different directions with different contributions due to different parts of the wire and things of this sort. We just want to focus on what's going on right at the center. We're never going to mathematically treat anything else. Now, direction-wise, you might have to know. So if I go, off to this part over here, so my application of the right-hand rule that we learned in the last lesson, B equals mu naught I over 2 pi r. So your thumb goes in the direction of the current, which right here is directly down, and your fingers curl around the wire. And so for this guy then, coming here, everywhere over here, it points out. Everywhere over here, the magnetic field it creates points in. Now if we go down here, so once again, put your thumb in the direction and then curl your fingers around. And everywhere above it, it points out. Everywhere below that part of the wire, it's going to point in. Come over here, put your thumb in the direction, curl your fingers around, and once again, everywhere on the left-hand side, it points out, and everywhere on the right-hand side, it points in. Should be noticing a pattern here. And then finally, one more time, at the top, the current's pointing directly to the left, curl your fingers around, and once again, everywhere below that point, it points, the magnetic field created points out, and everywhere above, it points in. And so what you end up is with magnetic field lines that point into the board everywhere around, and they're coming around and coming out through the center. And we only care in this case about what's coming out through the center. Now here's the rub here. So we figured out it was coming out by application of the right-hand rule we learned in the last lesson for current proceeding through a conducting wire. However, there's often a new right-hand rule specific for loops that's taught here. And it's simply just take your fingers and curl them around the loop in the direction of the current. And then your thumb's going to show you where the magnetic field is pointing right at the center of the loop. And your thumb is going to show up right at the center of the loop and everything. It's beautiful. Except it's not that beautiful, because if you notice, let's write this down and see why it's not that beautiful. So in this case, we're now going to have your fingers match up with the current, and we're going to have now your thumb match up with the magnetic field. That's the problem, right? So this is opposite of every other right-hand rule we've learned. We've been consistent in keeping your magnetic field with your fingers and the moving charge or current with your thumb. That didn't happen here. So this one's an exception. So in this case, if we use this right-hand rule again, we can wrap our fingers around the current of the loop, and right out the thumb is again where your magnetic field comes, but it is defined backwards, and it is commonly presented this way. This is not my special one or anything like that. So again, you could figure this out with application, again, of the right-hand rule at every point around the loop and figure out, oh, they're all contributing and pointing, coming out in this case, of the center, or you could use the new right-hand rule to figure it out very quickly. Cool, now similar to that, we also have an ideal solenoid here, and a solenoid is kind of a coil, a conducting coil of current. And so in this case, I'm going to have current flowing in right here, and then flowing out right here. And then right through the middle of this coil is going to be a magnetic field. Now it turns out in this one, we define things exactly as we did this one right here. And so if you coil around with a current with your fingers, your thumb will show you exactly where the magnetic field is in this ideal solenoid. And so in this case, if we look, it's kind of going around and around and around, and we got to figure out, is that this or is that this? And in this case, I can see that as the current, let's get the red marker out, as the current's coming around like there, that's going around this way, all the way down the coil, coming around this way. And so there's a magnetic field pointing to the right, all the way down, so through that solenoid. Now it turns out there's actually a magnetic field coming all the way back around, all the way around it. But it turns out the magnetic field that's coming outside the coils is fairly weak in comparison. But with all the coils, so numerous wires wrapping around with current going through all of it, I shouldn't say numerous wires, a single wire, but with current going through all the different loops of the solenoid, you can get a rather significant magnetic field right at the center of that solenoid. That's useful. These have applications in cars, these have applications in like MRIs. Technically, when you get an MRI, you're in the very center of a solenoid functioning as an electromagnet. And that's the magnetic resonance imaging, that's the M in the MRI there in that case. Okay, so now we understand the right-hand rules for both, and you might have to do a simple plug and chug as well, which is what we'll do next. First question says, what is the magnitude of the magnetic field at the center of a single loop of wire of radius 0.2 meters having a current of 8 amps? So here we're dealing with a loop, and we've got a straightforward equation here. So N mu naught I over 2R. And in this case, we've just got the single loop. And so N here is going to be 1 and kind of falls out of the equation. So mu naught's a constant. I meant to bring this up in the last lesson, but mu naught is a constant. Probably not one you have to memorize, but it's 4 pi times 10 to the negative 7. And the units on it can be given in a couple of different ways, but it's Tesla meters per amp, which is technically a Henry per meter as well, but we haven't dealt with Henrys yet, so we don't want to define it that way. And then times the current, which in this case was given as 8.0 amps. So, and then all over 2R, in this case, R being the radius of your loop. And in this case, we're told that straight up the radius is 0.2 meters. And from there, it's plugging and chugging. Now, there's a couple different ways you might approach this. You might leave it in terms of pi and things of that sort, or you might just let your calculator reduce it all down for you and things of that sort. But if you notice the units here, so here your meters are going to cancel, here your amps are going to cancel, and it's going to come out in Tesla just as it should for the strength of a magnetic field in SI units. All right, so I made the numbers nice yet again. So 8 divided by 2 is 4. 4 divided by 0.2, you can look at that one two different ways. So you can do 4 divided by 2 times 10 to the negative 1, or dividing by 0.2, same thing as multiplying by 5, or something like that. And again, you can just plug this all into your calculator. So, but 8 divided by 2 is 4, 4 divided by 0.2, it turns out is 20, 20 times 4 is 80, and so this is going to come out to 80 pi times 10 to the negative 7 Tesla, whatever that happens to be. So, and again, sometimes professors like to give you numbers that you can do without a calculator and leave it in terms of pi, which personally I kind of find annoying. So in this case, let's go and figure out what that is as well. I'm going to start this back from the beginning here. So we've got 4 times pi, e in my calculator to the negative 7, which means times 10 to the negative 7, times 8 divided by 2 times 0.2, all in parentheses. And we're going to get 2.5 times 10 to the negative 5 if we round to 2 sig figs. Tesla. Okay, so the other problem we're going to do is going to deal with the calculation involving an ideal solenoid. And it's going to say, what is the magnitude of the magnetic field at the center of a 0.50 meter long ideal solenoid composed of 100 turns having a current of 0.25 amps. All right, so in this case, the equation also involves mu naught here. Now you gotta be careful on this. So in this case, the number of turns and the entire length of the solenoid might be given, or you might be given them as a combination, the number of turns per length. You might not actually know the absolute length or the number of turns, but if you know that it's 100 turns per meter or something like that, you can plug that in as kind of this lowercase n right here. So, but in this problem, both the absolute length and the total number of turns are given. We'll plug them right into this top formula. And again, U naught's 4 pi times 10 to the negative 7. And again, that's Tesla meters per amp. Multiply that by N over L, which is 100 turns, over a length of 0.50 meters, and then times a current of 0.25 amps. I'm running out of room there. We'll squeeze it in. And from this case, again, I chose the numbers, made it a little bit nice. If you look, when you're multiplying and dividing a string of numbers, you can do it in any order. And personally, 0.25 over 0.5, I see that and I'm like, oh, that's a half. And 100 times a half is 50. And 50 times 4 is 200. And so this is going to come out to be B equals 200 pi times 10 to the negative 7. So, and once again, the meters are going to cancel, the amps are going to cancel, and it's going to come out in Tesla. And once again, though, I'm going to let my calculator do the heavy lifting. But I'm going to start it back from the beginning here. So once again, we're going to have 4 times pi e to the negative 7. So 4 pi times 10 to the minus 7 times 100 divided by 0.5 times 0.25. And now we're going to get 6.28 times 10 to the minus 5, which will round up to 2 sig figs, 6.3 times 10 to the negative 5 Tesla. If you found this lesson helpful, consider giving it a like. Happy studying.